Okay, so we talked about the confidence intervals for the population means. We had a couple ways of doing that depending on type of sample set we had and whether or not we had the standard deviation for the population. And then next we talked about the confidence intervals about proportions, essentially yes or no questions, or situations where where a certain percentage of people fell into one group and the rest of the people fell in another group. So now we're going to talk about a different topic that's a little different than those two, confidence intervals about the variance and essentially standard deviation. So the difference is when we did our confidence intervals for the mean. Let's do a different color here. We used the standard z table, which was a standard normal curve. To figure out what our values for z alpha over 2 were. When we did confidence intervals for proportions, we used the what sometimes is called the student t tables, and it was a set of tables that represented. So then we had t alpha over 2, and they were really analogous. So the t tables. So series of normal curves based on degrees of freedom. But now we want to do a confidence interval about the variance. And one thing that's different about that is when you take a sample of standard deviations or variances, unlike other data that the sample set would always turn out to be, we always would engineer it so the sample set would turn out to be a normal curve. The sample set of, let's write it here, sample set of the variance remember we always called it sigma squared for the population term, does not follow typically a normal curve. So the z distribution or the t distribution won't work for us. Instead, this looks a little different when you plot these things. Plot a couple of these. One might look like this. They're skewed a little. So they're not symmetric. We do have a way of solving this. Based on a family of curves approach, like we used with the t distribution. So I'll draw a family of curves here. And sometimes it might actually look somewhat normal. Let's get one more color in here. What color haven't we used? Good maroon. Purple might stand up. And there's actually, at one end of this family of curves, looks something like even that. We call this family of curves the chi-squared. Spelled something like that. So this is a chi-squared curve when the degrees of freedom equals 1. This is when the degrees of freedom equals 4. Maybe this is perhaps for 7. Here's 9. And maybe this guy is 15. So they start kind of acting in this sort of way. So notice the curves in general are not symmetric. So the approach we use for determining z or t alpha over 2 is not the same. Now degrees of freedom here is calculated the same way. It's the sample size minus 1. So what we'll need then is we're going to need a different set of curves. And that set of curves, the chi-square curves, is shown on your the tables that I've included, both earlier and here. And let me pull one of those over here. Okay, here's a chi-square table. This table is probably good enough for you to use on your homework. These are tough tables to locate on the internet, but you can find them if you look. Anyways, so the situation we're going to run into is we're going to have some distribution follows a chi-squared distribution, and we're going to be in the same boat we were in before, where we want to solve and look for solutions that are associated with, say, maybe a 95% confidence interval. So for 95% confidence interval, our alpha is going to be 0.05. And since this represents the area outside of 95%, so in a chi-squared distribution, maybe it'll look something like this, where this internal part is 95% of our data. Alpha over 2 is 0.025. But notice that this chi-squared distribution will pick a chi value based on the area to the right. So when this is 0.025 and we're trying to find this chi-squared, so might call this chi-squared. To the left. That's pretty easy to do. It's just 0.025. So we pick out our value here, 0.025. Now, our degrees of freedom for a problem, let's say that n, I'll put here say because this is just I'm just going to randomly generate a problem, say n equals 18. then the degrees of freedom is going to be n minus 1 is 18 minus 1 equals 17. So this value here represents degrees of freedom. And we come down here to 17, cross-reference that with 0.025, which is this column. It's kind of difficult to determine that, but it is this column. And we have 7.56 is the value. Okay. So now if we want to figure out what this one is over here, to represent this area, this is also 0.025 of the area, but you can see that it's not symmetric to this side, so this value over here isn't going to be a symmetric value. So chi-squared right, if we're going to figure out what this chi-squared value is, we need to look at the chart, and the chart only reports the area to the right. So what we're going to have to do is we're going to have to do a calculation. We're going to have to do 1 minus 0.025, which equals 0.975. And so that is the area to the right of this. And so we're going to look here for our second number, and our second number looks to be 30.19. So we might call this chi-squared of 0.025, and this would be chi-squared sub of 0.975 with respect to this chart. Now different charts do things differently, but this chart should be good enough to do your homework and to understand the concept here that we're doing. So now we're going to have our chi-squared values, and we're going to set up an equation for the confidence interval around a variance, and I'm going to do that in the next video.